Okay, guys, so today we have Carolina Figueiredo from Princeton University, and she's going to talk about this paper, Multiparticle Factorization and the Rigidity of String Theory. So thank you, Carolina, for accepting our invitation, and please go ahead.
Okay, well, thanks a lot for having me. Unfortunately, I can't be there in person. Portugal is definitely the country that I go to most frequently. So hopefully there will be a chance for me to visit in person. So today I'm going to be telling you about this work that came out at the end of last year that we did together with Nima, Cliff, and Grant, where we sort of initiate a study of imposing the constraint coming from consistent multiparticle factorizations to sort of exclude possible deformations of string amplitudes. So the paper is fairly short, which I think ends up making it kind of lack some kind of part of like the actual details and the explanations of how to actually implement these requirements for multiparticle factorization. So today I hope I can give a sufficiently practical overview of how to actually implement this so that you can go away and kill your favorite string theory deformation after this talk. Okay, so well, this is a Zoom talk, but please interrupt me as often as you want because I hope that's still possible. Okay, so the plan is going to be the following. So we're going to start with just a quick motivation. We know that string amplitudes are kind of these fascinating objects that seem to have a load of fascinating properties, like in a way that it's hard to even believe that it's possible. And so the question of how rigid these structures actually are is a very natural one to ask, and it's actually gained some renewed interest over the last few years. So on the second part, we're going to sort of switch to just kind of understand the actual worldsheet integrals that appear when we compute a string amplitude and understand why these sort of asking for this consistent multiparticle factorization was something that was slightly hard to impose before. It turns out that the way we usually parameterize these integrals in terms of the worldsheet coordinates makes hard to access these massive residues, the massive string resonances. And that's what I'm going to try to convey and explain how this problem is solved by introducing these U variables, which are and that allow us to write the string integral in a different way, and in particular, more specifically, a different way to parameterize the integral, which goes by the name of positive parameterization, which is something that Nima and collaborators worked out over the pandemic for any order in the topological expansion. So really not only tree-level amplitudes, but as well as loop level. But today we're going to be focusing purely on tree level. And then ultimately, once we have this new parameterization, we can extract these residues efficiently. We will understand how we can use them to sort of impose this consistent multiparticle factorization. And we did even kind of rebuild the string spectrum from the bottom up. And at the end, I just want to give a quick overview of how these sort of new variables, these U variables, actually provide us a perfect playground to build sort of simple string deformations and how to kill them using this sort of the same constraint coming from multiparticle factorization. Okay, so just a brief review. As I just mentioned a few seconds ago, string amplitudes are often like thought about as this having the best of all worlds, and they sort of have all these very nice properties in a single shot. Maybe the most striking one is the fact that they give us a consistent way of reaching high energies, passive validity of GR. And they don't do this in any way. In particular, if we like reach high energies at a fixed angle, they're actually exponentially soft. But what's even more surprising is that they can reach this exponential softness while still being polynomially bounded in the Regge limit. Okay, and this is what ensures that they describe causal processes. And on top of that, even though they have this infinite tower, so they have this infinite tower of higher spin states, which we know that by themselves are inconsistent, and somehow, exactly because there's an infinite number of them, they conspire in a way that still allows the theory to be unitary. Okay, so these are very striking features that make the question of whether these objects are indeed unique a natural one to ask. And people have asked this many years ago in a little bit of a more and followed a little bit of a more formal approach to answer this question. But over the last few years, people have been trying to understand whether they're unique or not, by just asking whether we can deform away from them, right? So to coming up with some other ansatz that shows the same striking features and ask whether it's consistent with the physical principles that we know. And it's true that we've seen a lot of examples of such deformations, and most of these are defined for the case of the most simple amplitude, the 4-point amplitude. So for the open string, this 4-point amplitude is given by what we call the Veneziano amplitude. So it's a simple beta function, depending only on S and T. And people have proposed deformations of this object. Maybe the earliest attempt of deforming it was proposed by Kuhn in 1969, introducing the Kuhn amplitude. And for a while, there was not any activity in this direction, but over the last 3 or 4 years, a lot of different people have been studying it, including some possible generalization for higher points. But also in a little bit of a different approach, multiple people over the last few years have tried to understand whether imposing some sort of EFT constraints and requiring the positivity of the Wilson coefficients, whether we can sort of restrict the space, like the space of theories that we can be describing, imposing like unitarity constraints, requiring the asymptotic behavior to match that of string amplitudes, and even just, we know that string amplitudes satisfy these relations called monodromy relations. All these are natural constraints to ask how restrictive they are and whether they allow us to land uniquely on string amplitudes via the usual bootstrap approach. And it turns out that more or less the conclusion is that, strictly speaking, at 4 points, there seem to really be many ways to deform the amplitude that is still compatible with the physical constraints that we're talking about. So here I have a very simple example. I just want to give you a little bit of a feeling of how actually restrictive these constraints really are. So I'm just so I've set alpha prime to be equal to 1, which I'll do mostly in the rest of my talk. And we just are simply deforming this beta function by what's called the Regge intercept, this parameter that we call alpha naught, okay? So of course, this object's still going to be exponentially soft. That just comes from the fact there's still this ratio of gamma functions and still polynomially bounded in the Regge limit. But we can ask, is it still unitary? So at the level of the amplitudes, the way we usually check unitarity is via the sort of evaluating the partial wave expansion, which tells us that if we go on a particular residue, so if we evaluate at S equals like minus n, right? So the nth level, then we should be able to expand our answer in terms of what are called the Gegenbauer polynomials, right? Which depend explicitly on the space-time dimension and on the scattering angle theta, right? And unitarity tells us that the coefficients that appear multiplying these polynomials should all be positive. And the intuition for this is just because we can interpret these coefficients as the mod squared of the 3-particle amplitudes that are coupling the external states to the internal state of spin S, right, at 4 points. And it turns out that this constraint is already pretty restrictive. So just starting from the simplest case where we talk strictly speaking about the Veneziano amplitude. So we set alpha naught to be -1, which tells us that we're scattering a tachyon in the signature that I'm picking. Okay, so now the 4-point answer takes this form. And just by asking for partial wave unitarity at level 1, so we extract a residue when S is equal to -1, then we get this kind of polynomial in T. And as usual, we go to the center of mass frame so that we now introduce the dependence on this scattering angle, cos theta, where we can write T in the following way. And so if we plug that back in here, then we get this polynomial in cos theta, okay? So, and now we can, of course, like rearrange this so that it like explicitly becomes manifest that we're expanding in the Gegenbauer polynomials. And so we have this first part, which comes from the Gegenbauer polynomial associated with the part of spin 2. And while we have this first one, which corresponds to the exchange of a scalar, okay? And so, which is just a constant. And so by demanding that this coefficient has to be greater or equal than 0, we already have like the 26 appearing, right? Just by asking for this very simple constraint. We're not nailing it down to d equals 26, but we already see that it has to be smaller or equal than 26, okay? And doing following exactly the same procedure for the Regge intercept to be equal to 0, we get that d has to be smaller or equal than 10. Which kind of rings a bell and maybe seems to connect a little bit with what we will get for the superstring. Anyway, it turns out to be a little bit of a coincidence, but the sort of point that I want to highlight is that by sort of requiring these constraints, we can already start making plots like this and see that indeed the sort of region of consistent dimensions that we can be in can be highly kind of reduced just by imposing these very simple constraints coming from partial wave unitarity. Okay. So the question that sort of remains to ask is whether this freedom that we observe at 4 points is still there for the case of higher point amplitudes. And today I'm going to be talking about two simple deformations that are defined for for all points, right? Which is, well, very important for us to be able to do this check of multi-particle factorization. We need to have a definition of the amplitudes for arbitrary number of points. Well, at least 5 or 6 for what I'm going to say today, but in general, anyway. So the first family is called these bespoke amplitudes, which were revisited by Cliff and Grant in a paper early last year. And I'm not going to go much into detail into what these amplitudes really are, but the idea is just that originally my amplitude depend on some particular Mandelstam invariants, right? These are the Mandelstam invariants entering, and what I do is I just allow I change it so that I can have a function that is composed with the Mandelstams. Okay, and this slightly changes the amplitude, but still preserves the properties, like to still have an infinite tower of spins, and so on. And then the other sort of deformations I will be talking about in the last part of my talk is the ones that we introduce in this paper, which we call P-view-like deformations. Okay, so both of these, as I just mentioned, they still have the usual properties of string amplitudes, including the infinite tower of states, and they make manifest the factorization on the massless poles at finite alpha prime, okay, which is non-trivial. It's easy to ask for something that factorizes on massless poles in the field theory limit, but at finite alpha prime, while we have all the spectrum, this is still non-trivial, and these two deformations do it. But the question that we want to ask is what happens for the massive resonances, okay? And the sort of main bottleneck in asking this question is really accessing the higher spin residues in the string spectrum. Okay, and so that's what we're going to move on to now. So here I have the sort of usual integral that appears when we're talking about tree-level open string amplitudes. So it is an integral over an n-dimensional space of the z's, which are the world sheet coordinates, where we mod out by the world sheet symmetry, which in this case it's an open string, it's just SL2R. Then there's this prefactor over here that just goes by the name of, we usually call it the Park-Tiller factor. And then this last product over here is called the Kobe-Nielsen factor, and it introduces the dependence of the amplitude on the momentum of the particles that we're scattering, as well as the string constant alpha prime. Okay, so these zij's are really the difference of the z's, which are the coordinates in the world sheet. So usually these integrals go with like pictures like this, where we're just scattering describing the scattering of an open string, maybe time is evolving in this direction over here. But usually we use the world sheet conformal symmetry to just do a conformal transformation and to map this diagram into a disk with like 4 marked points on the boundary for this case, okay? So these are the sort of surfaces that we care about, disks with marked points on the boundaries, since we're at tree level. And we see that automatically just by doing this, naturally, we're talking about a particular color ordering of the indices, right? Which at the level of the integral translates into the fact that the z's have to be ordered. So we're integrating over the region where z1 smaller than z2 all the way to zn. Right? And the way that we have to mod out by this world sheet symmetry, the SL2R, we usually say we just gauge fix. So we use the symmetry to fix 3 of these points to some special places that we can choose. And the canonical choice to do this is to say that the first one goes to 0, the n-1 goes to 1, and the n goes to infinity. Of course, you can choose them in different ways. You'll have different representations, but this is the one that I'm going to be looking at now. So effectively, after I fix the z's, I have an n-3 dimensional integral. And what I'm going to try to show you is that this particular representation makes it hard to access the singularities, okay? But before proceeding to that, it's worth just spending a few minutes actually thinking about what are the singularities of these integrals, right? And so exactly because I'm talking about a color-ordered amplitude, we know that even just by thinking about what happens in the field theory limit, we should not have poles when any dot product of pi dot pj is equal to 0. Instead, we have poles when a subset of adjacent momentum becomes on shell, right? So when we have that the sum of pi, I plus 1, all the way into j minus 1 squared is equal to minus m squared. Okay, and to sort of keep track, what are these, because these are the sort of things that appear as propagators in planar diagrams, which is all that we have when we fix a particular color ordering on the outside. Okay, so a nice way of kind of just thinking about these variables that appear as singularities is by considering the momentum polygon, where we just list all the momentum of the particles that are involved in the scattering process. We list them tip to toe. And this closes into a polygon because we know that they satisfy momentum conservation. So if we sum all the momentum, we should get 0, right? Okay, and so naturally, these variables that we care about just automatically become the length squares of the chords of this polygon, okay? Because so this curve I can just obtain by summing this momentum, and so the length squared is really the variables that we care about, okay? And so basically, we will think about the propagator that can appear in these planar diagrams as being the chords associated with these polygons, okay? Okay, great. So, but now in the expression that I started with, this one over here, we see that to begin with, our dependence on the dot products is really in any pi dot pj, not in this particular kind of nice combination that automatically maps to the singularities. So a natural question is asking whether there's any change of variables that I can do that will make this dependence manifest so that I can study the singularities in a simpler way. And this can be done by introducing these SL2R invariant cross ratios, which are exactly these U variables that I mentioned in the beginning, where I define Uij associated to 2 particular mark points on the boundary. And so I usually label them by the corresponding curve in the disk with these particular cross ratios of the Z's, okay? So this cross ratio is built in a way that it's invariant under the SL2R symmetry. So it's also a natural object to try to express our answer on. And so by doing this, what happens is that I can just recast the Kobe-Nielsen factor in terms of this product over here. And I end up making the dependence in these Xij's manifest exactly as I wanted. And so in the signature that I'm picking, the massive poles that I want to access happen when alpha prime Xij's are equal to negative integers. Okay, and also at 0, of course. Okay, so now I want to spend a little bit of time talking about these U variables per se and why they're natural objects for us to try to write our answer in terms of. So we've just seen their definition in terms of the Z's as these SL2R invariant cross ratios, and it's a non-trivial check that this particular definition makes manifest that these variables satisfy a set of quite non-trivial nonlinear equations, which are called the U equations. But in summary, these equations tells us that if we pick a particular Uij, which is associated to some curve on the disk that goes from I to j, and we take the product over all the curves that cross ij, so these km's are, I call them incompatible just in the sense that they cross, okay? This has to be equal to 1. And what's even more non-trivial, if I just gave you this set of equations, there are as many as equations as variables, right? Because I have 1 for each Uij, but still the space of solutions is still n-3 dimensional. Well, this should not be surprising because we just saw that the U's can be parametrized in terms of the Z's, and the Z's, we know there are n-3 of them after we gauge fix, right? So this is just telling us that there's an n-3 dimensional space of solutions, and that on top of that, if I ask for all the Uij's to be greater or equal than 0, that is the case that's just automatically satisfied when I pick my Z's ordered, then to satisfy this equation, I can see that all of them have to be smaller or equal than 1, because it's a sum of things that has to add up to 1. So basically, I know that these variables all lie between 0 and 1. And another very nice feature that becomes obvious because of these equations is that these Uij's make the factorization of the full string answer manifest. So as we've just talked about, we know that the singularities happen when these Xij's equals negative integers, and in particular 0. And what happens is that when I evaluate the integral on this locus, it develops a singularity exactly near the region where the Uij is equal to 0. Okay, so we can understand this mapping. And if I look back at the U equation, I see that when a particular Uij goes to 0, then all the UKMs that cross it, so the incompatible ones, have to automatically go to 1, right? So that this equation is satisfied. Okay, so this is what's called the binary behavior of these variables. And this then makes manifest that the product of, so the Kobe-Nielsen factor, which is the product of the U's that appears in the string amplitude, when I go near the locus when I get a residue, right, then my integral is going to localize exactly in the region where the Uij goes to 0. And so this tells me that this product is going to end up factorizing into exactly the product of all the curves that live, strictly speaking, on the left part of my disk, and strictly speaking on the right part of my disk, because all the ones that crossed just go to 1, right? And this is exactly what we expect. So the amplitude factorizes into the product of the lower point amplitudes, just as we wished, okay? So this is just some nice features of these variables. But so far, I've only told you that we know like how to parameterize them in terms of the z's, right? And now we're going to try to understand why this particular parameterization is not ideal and makes it hard to access the singularities. And to do this, we're going to look at this, the 5-point case in detail, right? So if I just expand out my answer, so I fixed z1 to be at 0, z4 to be at 1, and z5 to be at infinity. And if I rewrite my integral under this gauge fixing, I have this, this is the following result. So I have these 5 different monomials here to different in the exponents, I have different dot products of momentum, where we can already note that, for example, here we have the dot product of P1 dot P3, which we know does not correspond to any pole because P1 and P3 are not adjacent, right? So like already there, we know that the exponent does not correspond to any pole, but we can still ask, what are the singularities of this integral? Okay, and we can see that the space of singularities, we can just look at what are the sort of branch cuts that appear from each of these terms. And these are going to produce 5 different straight lines in Z2 and Z3 space, right? So the first one, so from these 2 ones, we get the lines at 0. So this one and this one. Then these 2 gives us 2 straight lines at 1. So this one and this one producing the square. But then we have this final equation, which just gives us the diagonal straight line, this one over here. Okay, so but now, well, we're not really integrating over the whole space because we know the z's are ordered. So in particular, z2 has to be greater than 0 and smaller than z3, which is also smaller than 1. So it tells us that the integration region that we're considering is really this smaller triangle over here. Okay, well, but now we're at 5 points. So we know that, like just by even thinking about the field theory case, right? We know that each diagram has 2 propagators. So we should at most have double poles, right? Where we can have 2 different propagators going on shell. And that's sort of what happens in this intersection over here, right? We have the pole corresponding to the P1 dot P2, which is a planar propagator. And we also have one corresponding to P3 dot P4. So this is okay. This would correspond to the double pole that we'd expect for a particular diagram. But something more special happens in these 2 points, because now we have the intersection of 3 different singularity regions, which basically, well, and on top of that, this geometry that we get is just a triangle, which seems to sort of suggest that we only have 3 singular points, which we know is not the case, because at 5 points, there are 5 different diagrams that should contribute. So we should really have 5 different double poles that we could access. Okay, so something is off here. And the problem is exactly associated with these 2 points, where we see that as we approach these regions, there are 3 different terms in our expression that start becoming relevant. They are making the integral singular, right? And when this happens, what it tells us is that we need to do the following. We need what's called a blow up. So just to give the concept of blow up is just a fancy word for something which is really simple. Like if we have some function that depends on x and y, right? Like some polynomial in x and y, then if we want to take the limit where x and y go to 0, then we can just take it automatically and everything's okay. But if instead this function is a function of x and y, but also depends on the ratio x over y, now we need to take this limit carefully, right? We need to sort of map out what are all the possible ways that we can approach the 0. Okay, so we have to do exactly the same thing here. And so to do this, like we just want to zoom in what happened near these points. So where both Z2 and Z3 are equal to 0. And so we just do a change of coordinates in this region where we say, okay, let's say Z2 is equal to epsilon times Z and Z3 is equal to just epsilon, okay? So where both epsilon and Z live between 0 and 1. And by doing this, we automatically ensure that Z2 has to be smaller than Z3 as we want because of just the underlying order of the punctures. So really, we can think of Z as the angle by which we are approaching 0 over here. Okay. Okay, so if we do this, so if we plug in this change of variables back into the string integral, we see that the 5 different monomials that we had before turned into now monomials of epsilon and Z. And something nice starts happening as we see that now the power appearing in epsilon becomes exactly a sort of a planar variable, as we would expect for poles of these planar diagrams, right? Okay, and we have some different ones. So if we map them back to now the space Z epsilon space, so we see we have a singularity at epsilon equals 0, Z equals 0. We also have one at 1 for both of them, and which correspond to like the square, just like we had before. But now we have these further hyperbola, right? Like this sort of curved, this sort of curve over here. Okay. But once more, we're just using this change of variables to study what happens when both Z2 and Z3 get small. So really, we only care about what's happening in this region, right, where epsilon's small, because that will sort of assure that we have both Z2 and Z3 small. And we see that instead of having just a single singularity, we see that we now have two different singularity points. So this is what happens when we do a blow up. We approach the singularities in different ways, and we see that actually instead of a single point, it blows up into this intersection of three straight lines, right? Where we now start seeing the singularity associated to the planar pole P1 plus P2 plus P3, okay? And note that the singularity associated to this extra line is just basically given by the sum of the momentum that enter in the two straight lines that intersected, right? Okay, so we've done this for this first part, but of course we need to do exactly the same thing for this other problematic point. And so if we do this for both regions, then the original triangle gets blown up to a full pentagon, like the one that I have here, right? So if I do exactly the same thing, then I'll get a further singularity associated with the other possible planar pole that I can have, which is P2 plus P3 plus P4. Okay, and now it looks fine, right? Because I know there should be 5 different diagrams, each of them corresponding to a possible double pole, and that's exactly what this pentagon is describing, right? So now I've been able to map out the singularities of the full integral, right? And so to see this in detail, we can actually we can see this explicitly. So if we look at this particular vertex, we see that we have the things that correspond to P1.P2 and P3.P4, which will correspond to the singularities associated with this planar diagram. So here I'm drawing diagrams, but really you can translate them into the full world sheet. Well, it just gets really stretched in these directions. It's just that the massless poles of the string amplitude correspond to the regular poles in the field theory limit. Those are the ones that survive. They just get extended to the infinite tower where these x's become negative integers. But so this is just schematic. Anyway, then we can see that this further kind of point that we obtain after the blow up is like, so it encodes the singularities associated to P3.P4, which will correspond to this propagator, and the one correspond to P2 plus P3 plus P4 squared, which will correspond to this one. See, so these are just different diagrams that are both compatible with the external ordering that we're picking for our particles. Okay, so we do the same thing, and we can like just discover all the diagrams corresponding to each different vertex of this geometry. Okay, but in general, we see that to access these the blue point singularities, we needed to first find a blow up, which in general it's hard because so this was only at 5 points, but in general, if I'm at higher points, I'm gonna like at around each singularity region, I'm gonna have to find a different blow up, do the blow up there. And well, the singularities grow with the number of Feynman diagrams, which grow exponentially as I make the number of particles as the number of particles grows. Okay, so this becomes extremely hard if I'm trying to probe higher point string amplitudes. So the goal is to see if there's any different parameterization of the string integral, so in particular of the UIJs, that makes these blow-ups automatically. So that just does the correct thing in all the boundaries of the integration space that I'm taking, so that I can probe all the singularities in a simple way. And it turns out that the answer is that such a thing does exist, and it goes by these names of this positive parameterization, where I consider that the u's are really functions of the different set of variables that we call y's, okay, where these y's range from 0 to infinity, and that's why they're called positive parameterization. Okay, so all the singularities of the integral are going to be mapped to some u going to 0. And what happens is that in terms of these y variables, the regions where the u's go to 0 corresponds to just the boundaries of the integration domain in y, right? Where the integral ends up localizing when I'm just extracting the residue, okay? And so we can just easily extract the residues just by going to a particular boundary with no need to do any further blow-ups. So this is the idea. Okay, so I'm not going to be able to explain in detail exactly the full details of this positive parameterization. There are like a series of papers by Nima more recently where these are explained, and more will come out in the future. But the sort of, it does have kind of a deep origin, but what I'm going to be telling you about today is really just sort of a recipe of how to obtain this parameterization, okay? And to get this parameterization, it really comes out of a problem about curves on surfaces. So in this case, we're at 3 levels, so it's really about a problem about the curves on the disk. Okay, so to define the disk, so to define the surface, we start by providing a triangulation. So a way of like just dividing our disk into triangles, like we've done here, right? A surface is really what results from gluing triangles together. So by providing a triangulation, we define the surface. And to each triangulation, we can sort of dualize and get a corresponding diagram. So, and to do this, it's a simple thing. That we do is we plunk down a vertex inside each triangle, and this sort of defines what is the dual diagram to the surface. And we see that the propagators entering in the diagram exactly sort of correspond to the chords that we have in our disk. Okay, so this is sort of the connection. So the chords that appear in the triangulation correspond to some of the propagators of the diagram, and the full triangulation really defines a diagram. But another way of talking about the surface is by thinking about what is called this fat graph that I obtained just by starting with this diagram here, and I consider fattening the legs. So I draw the corresponding what's usually called the ribbon graph that we usually draw for when we're talking about color theories, right? This double line notation. And here I've like shaded these regions to sort of make it manifest that these two objects can really be seen as the same. If I consider shrinking the shaded regions to points, then I'll land back on the disk with the marked points on the boundaries, okay? Sort of the key thing with that regards this positive parameterization is that for each triangulation that I pick of my surface, I have a different parameterization of the u's in terms of the y's. So there will be a particular set of y's that are naturally tailored to the triangulation that defines the parameterization. And what happens is that the singularities corresponding to the propagators going on shell are going to be mapped to different places in the boundary of the integration space, depending on the parameterization that I pick. So I'm going to make this concrete now, and we're going to sort of automatically jump into the sort of output. So once we find this parameterization, what do the integrals look like? So this is what they look like. So the sort of integration measure becomes this d-log form in the y's, where again, we have the y's are naturally associated to the propagators appearing in the triangulation. So for example, at 5 points here, I would have y13 and y14. Okay, so we have the d-log form in these y's. And then we have the same Kolbe-Nielsen factor that we had before, where now the u's are functions of these y's, as I'll define in a second. But what matters is that when I replace these u's in terms of the y's, the dependence on the kinematical variables associated to the propagators that appear in the triangulation is really simple. It just completely factors out so that I can like write this particular term. And then the remaining piece looks like some polynomial of the y's with some exponents that are just pi's or pj's. So to have a concrete example in mind, the 5-point answer can be written as follows. So again, I'm picking the triangulation corresponding to y13, y14, and I have this d-log form here in both variables, so dy over y. Then I have the simple dependence on the x's that appear in the triangulation, y13 to the x13 and y14 to the x14. And I have a bunch of simple polynomials in the y's, where now the exponents are dot products of non-adjacent variables. So these are not x's, right? Like these ones are just dot products of non-adjacent things. And this is going to be, generally speaking, what the integrals will look like. Okay? But so, one thing that this representation makes manifest is that if I take one of the x's in the triangulation to be negative, right? So I consider these exponents to be negative, then this integral becomes singular in the region where y13 goes to 0, right? Because this is just going to make contribute to a dy over y to a power greater than 1 in the denominator, which tells me that this becomes singular near the region of y equals 0. And so it turns out that, so this is a simple computation, but we can show that to extract the residue, so the coefficient that multiplies the pole at arbitrary levels when the when these x associated with the propagators are evaluated at negative integers, is simply what we get from just extracting the residue of this form after we evaluate at xp equals negative integer, but exactly in the region where y is equal to 0, because that's exactly where the integral develops the singularity, okay? But just to make this clear, of course, this form contains the information about all the singularities. The thing is that for x's that are not in the underlying triangulation, the singularities are going to be mapped to different regions to different boundaries of my integration domain. Okay, so some of them happen when some y's go to infinity and so on. But we can access all of them without needing to do any further blowups. But the even sort of nicest feature is that if I want to study the singularity associated to a particular diagram, then I can always pick a parameterization that is tailored to this diagram. And then for this particular parameterization, I can extract the residues really easily. So this is the sort of general procedure that we can follow. Oops, sorry. Okay, so this is the sort of the way that we can proceed. Okay, so that's, sorry. Okay, so let's see. So before I proceed to explain how that goes, I'm just going to quickly go through like a recipe on how to obtain this positive parameterization of the use in terms of the y's. So the way to do this is, let's say we're again at 5 points, we've picked this underlying triangulation so that we have this kind of fat graph. And the first thing that if I want to obtain, let's say the u associated to curve 2, 5, then all that I need to do is, well, I start by labeling all the edges associated inside the fat graph. We can label them in any way we like, but the way that I'm labeling them is just by sort of using the shaded regions that they are bounded by, right? I hope this is obvious. And so further, to the internal roads, to the internal edges of this fat graph, I associate the variables y13 and y14, just like I did for the chords in the triangulation, okay? And so what I do is I start by drawing the curve 2, 5 on the fat graph, right? So 2, 5 in this case is the curve that like starts between 2 and 3 and ends between 5 and 1. And I can see this is correct because what the rule is that if I tilt it counterclockwise, then the two ends will eventually touch 2 on this end part and 5 on the other part. So that tells me that I'm talking about curve 2, 5, okay? And then the next step is to sort of encode the information about the curve in a way that if I just handed you this information, you could rebuild the curve in the fat graph. So this is what we call like writing down the word associated to the curve. And to do this, all that we're going to do is we're just going to keep track of what is the path of the curve inside the graph. So looking at the curve, we see that it starts in like this edge 2, 3. And we see that as it reaches the first intersection, it turns left. So we like go up and right that we turn left into like edge 1, 3. Then it turn right here in the second intersection into 1, 4. And then it turn right again into 1, 5. Okay, so this information in principle lets you rebuild the curve even if you did not have the surface with you. Okay, and so now to get the parameterization of the u in terms of the y, we need to sort of further define. So this now looks a lot like black magic. It actually has a deep reason, but that I can't go into. But that is like, if you're interested, you can see in these like papers. But I'm just giving you the very simple, it's literally a 3-step recipe to obtain the parameterization. And all that I have to do is define this matrix associated to turning right and a matrix associated to the turning left. And then I just multiply these matrices as my word tells me to. So if I look at the word, I see that I start in 2, 3 and I turn left. So I take matrix turning left. But now 2, 3 is a boundary road. It's not associated to any inner edge, right? So I have to evaluate it at 1 because there's no y associated to this road. But then once I turn right at 1, 3, I know that now I do have a y variable associated to this inner edge. So now I have matrix right evaluated at y13 and then matrix turn right evaluated at y14, as the word tells me to do. Okay, so this is a product of a 2 by 2 matrix. So in the end, I have also a 2 by 2 matrix. And then the claim is that the u variable is going to exactly be the ratio of the CB over AD, which are all polynomials in the y's. So by doing this, we can see that for the curve 2, 5 in particular, we get this ratio of simple polynomials in y13 and y14, okay? And so in general, here I summarize what we get by following exactly the same procedure for all the 5 different u's that we have at 5 points. And already there are a few checks that we can do. So for example, I've told you that, so since I'm picking the triangulation that has x13 and x14, I can check that like when x13 goes to 0, I expect to develop some singularity near the region y13 equals 0. And that's exactly when u13 goes to 0, as I expected. And the same thing also holds for y14, okay? And then on top of that, I can check that this particular parameterization satisfies the u equations. That's maybe the most non-trivial check that I can do. So here I have an example. So if I take u13, and then I sum the product of the incompatible ones, which in this case is just 2, 4 and 2, 5, then there's some magic cancellation that like proves that indeed they actually add up to 1. Okay, so this is going to be true in general, and this is the way that we find this parameterization. And so in general, if we want to access some like higher point residue, for example, at 6 points, we start having some more interesting topologies. So in this case, if I wanted to access this residue corresponding to this star-like topology, what I need to do is pick the parameterization of the u's in terms of the y's that explicitly depends on the y's associated to the propagators that appear in this diagram. So x13, x15, and x35. And then to get this residue at these arbitrary levels, all that I need to do is extract just the residue when the y's are equal to 0, where I evaluate my function at the respective levels. Okay, so this is extremely simple, and this allows us. Yes.
Is there any geometrical interpretation of, like, if you want to choose 5 independent, or in this case, I suppose more 8, I think, UIJs, is there any way by drawing these curves that you were drawing that you see that this should go for something which is in like linear dependent on some other thing, and then you
Yeah, you
just
can, like, so from these rules, you can automatically see that they were going to be linearly dependent. So the U, for example, 1, 3 is going to be linear in Y1, 3, just as I shown here, right? Like this, is this what you're asking? Like U1, 3 is linear in Y1, 3, and so is U1, 4, right?
I mean, you can draw a lot of these different curves, right? In the previous slide,
Yes.
you have this specific curve 2 to 5, but you can draw many others, and then you can
Yeah,
see a
yeah, and
persecution.
those correspond to different U's, right? Like you need to draw all of them, and all of them map to the corresponding U's.
But is there a way by just drawing this curve that I see, okay, these are independent, I don't need to draw anything else?
Yeah, well, so because basically the curves, like each curve on the graph maps to a chord. So each curve uniquely maps to a chord in this diagram, and all the chords correspond to all the possible planar variables that I can have.
Mm-hmm.
So like basically we know there are as many U's as there are curves on my surface, right? So from like any way that I can connect to I and J, right? Like in this disk with marked points on the boundary, and they uniquely map to like the set of curves that you need on there's a unique map between the curves on this diagram and the curves that you can draw on the disk, right? Which is exactly in this way that I was describing, that you just tilt it to the left. Is this clear?
Yeah.
Okay, so you can, like, yeah, you do that for all the possible curves that you can draw, and they will correspond to all the UIJs that enter in the string amplitude. That is the idea. Okay, so now let's see how this goes so now that we have access to these residues, we can sort of start matching them to the possible level of what are the 3-point structures that appear, and with this kind of rebuild the string spectrum from the bottom up. Okay, so what I'm going to be talking about today, I'm going to start at 5 points, but I'm always going to go just up to level 1 for simplicity, and that's also what we do in the paper. And we're always considering the scattering of massless states on the outside. Okay, so at 5 points, just like we always have just this simple topology, all the remaining ones are just cyclic rotations of this one. So we see that we have two, like at this vertex, we have two different 3-point structures where two massless scalars couple to a massive one, and two massless scalars couple to a massive spin one, right? So this, and then we have two different couplings for this, which should already be determined just by asking at 4 points, right? These are the couplings that would appear at 4 points. But then we have the sort of new vertex that appears at 5 points is exactly this one, where we have a massless guy interacting with two massive ones. And for this case, we can have 3 different possible structures, depending on whether we have 2 spin 0, a spin 0 and a spin 1, and 2 spin 1. Where when we have 2 spin 1, we really have 2 different structures because these are massive guys, right? So we can have these 2 possible structures appearing. Okay, and so what we do is we say, well, we can glue these 3-point structures using the usual like spin. This is just the spin sum rule that we have for when we're exchanging a massive spin 1, right? Where this m squared is really equal to the sort of the resonance that we're evaluating at. And so we can do this and glue these 3-point structures together and match it to what we get from the string residue directly. So by doing this at 4 points, we can sort of fix the first 2 couplings that appear, alpha and beta, right, associated to these 3-point structures. And then what we do is we sort of input these ones into the 5-point problem and ask if there's still a consistent solution for the remaining vertices, right? So the remainings that there are to fix are these 3 new ones that appear at 5 points. And of course, well, string theory is a consistent theory that factorizes consistently. So we find a solution where we have these simple values of the couplings. And so we then can extend this study to go to 6 points, where at 6 points now we have 3 different topologies. So this is what's called the half ladder and the twisted half ladder. So for these ones, we see there's no really new 3-point structure appearing. All the ones that we have for these 2 diagrams were already fixed before at 5 points. But we can still ask for consistency, right? This sort of checks the consistency between like multi-particle factorization. And we also have a new structure that appears for this last topology, which is the star topology, where now we have a vertex that includes 3 massive states, right? And now these kind of generate some more interesting structures for different types of them. But we now proceed exactly in the same way. So we input the results coming from the 5 points. We ask for consistency, and we also ask whether we can fix these other ones that come up in this new topology. Okay, and so by doing this, we get some other values of these coefficients. And so this sort of illustrates how we can really kind of build the strict spectrum from the bottom up, not only the spectrum, but also what are the couplings, right? So this, well, we're building it like exactly probing resonances. So we're not really doing out of, as usually people do, like using vertex operators. But I think the more interesting thing is that we're really just considering the scattering of the massless states. So we're accessing all the spectrum by just asking about the S matrix for the massless states, which are the ones that we exactly know that are stable, right? Okay, and so, okay, in general, what we present in the paper is that if we further allow some non-zero Regge intercept, then we can do exactly the same study and like just discover what are all the possible like 3-point couplings that I was just describing before. Okay, so this is sort of the first output that we can do by having an efficient way of accessing the residues. But in general, if we propose some deformation of string theory, this is also an information that we need. We need the information about the residues to check whether it satisfies this consistent multi-particle factorization. Okay, so there are 2 different routes that we can follow if we want to implement this constraint. Let's say that first we're given some deformation of the worldsheet integral, right? So like it's just written as it usually is, it's just some deformed version of it. So the first step to kind of implement this check is to do this change of variables where we go from the z's into the u's, and then for the u's, we find some parameterization in terms of the y's, right? They're tailored to a particular diagram in the way that we explain, and there we can easily just extract the residues and ultimately match them to the sort of possible 3-point structures to determine the couplings and ask whether there's a solution to this problem, right? Alternatively, there's some situations where just given the residues of the amplitudes a priori, which is exactly what happens for this family of amplitudes, these bespoke amplitudes, because the way they deform the amplitudes is by forming this dual resonant form where you're really just specifying the residues. So in this case, you're just given the residues a priori, so we can just proceed directly to do step 3 and step 4 and ask whether they're satisfied. And what we find is that it turns out that you don't really need to go to very high points, nor very high levels. So just using 5 and the 6-point topologies that I described before and probing the residues up to simply level 1, we can already rule out the simplest family of these bespoke models. Okay? So this is sort of one of the lessons. And now, to end, I would like to sort of just give a highlight of how these U variables can also have a little bit of a different purpose in life, as well as giving a nice playground to sort of just build simple deformations of these string amplitudes, and ultimately how we would go about killing them. Okay? So the first requirement that we ask for any possible deformation is, of course, to satisfy this massless factorization, right? This was the thing that we knew that all the bespoke ones satisfied. This massless factorization. So this is not super trivial because it's a massless factorization at finite alpha prime, okay? Which involves the massless factorization of the whole spectrum at the massless poles. In any case, the reason why these U variables are particularly nice to build such objects that automatically satisfy massless factorization is exactly because of this binary behavior that I told you about that comes because of the U equation. So we saw that when we set a particular Uij to 0, then automatically all the ones that cross it go to 1. So we can see that the amplitude nicely factorizes into the lower point amplitudes, right? So because when we extract a residue at the massless level, we have a simple d log form in the y, so we just have a dy over y. The residue that we get is simply evaluating this product when what happens when the uij go to 0, and because of these like binary property, the ones that cross it go to 1, so the product really splits into the 2 lower point objects, okay? And so we can ask, okay, so well, if I want to deform away from the regular string object, I can just simply multiply it by some like function, that we call this p of u. And it will still factorize as long as this function that I define is such that if I evaluate it in the locus where one of the uij's go to 0, then this function also factorizes exactly in the way that I expect the amplitude to, right? I hope this is clear. So I want a function that then factorizes into the lower point functions associated with the two lower point problems that appear when I cut the surface through I and j. Okay, so this ensures automatically massless factorization, but the reason why massive factorization is not ensured, I'm just going to try to sketch it over here. Is it like, so to do this, let's look at what happens if we're probing the singularity associated to an x in the triangulation. So we see that, so for those x's, the dependence on the y's looks like something like this. So if we evaluate at x equals 0, then this term just disappears. And so the residue, right, like, so we have already a 1 over y here. So the residue is whatever we get here evaluated at y equals 0, right, the residue of the form. But if we evaluate it at xp equals -1, then we're going to get, the form becomes like what's called polynomially divergent in this region, which tells us that if we want to extract the residue, we actually need to take a derivative. So get the linear piece in yp near yp equals 0, right? So we need to expand whatever we have left up to linear order. And so to going at xp equals -2, then we need to expand to quadratic order and so on. So this now involves some derivatives of the u's and not just what happens exactly when the u's go to 0. That's why the massive factorization is not guaranteed. Okay, now I'm going to end by just providing a simple example of a P of U that sort of satisfies this requirement and so gives us a deformation that satisfies massless factorization. As you'll see, this is a very simple P of U, but we believe there are many more out there to explore. This is just how we would go about building one. So to do this, we start by considering the set of all the triangles that live inside our n-gon, where here our n-gon is again sort of just labeling associated to the momentum polygon of the particular scattering process that we're considering. Okay, so these triangles are defined by just a pair of 3 vertices that live inside the polygon. So these 3 vertices can form like some triangle that lives, strictly speaking, inside the n-gon, or also like one of the edges corresponds to a boundary, right? Or 2 of them. Okay, so the polynomial is the following. So we take the product over all the triangles that lie inside the polygon, and then for each of these we consider 1 plus this deformation parameter that we call g, and then we further take the product over all the 1 minus uij, where I and j are both are all the possible sort of pairs of indices that appear inside the triangle. Okay, so once more, this g can really be thought as a deformation parameter, because we see that if we set g equals 0, then this polynomial just becomes 1, and so we get the usual string theory answer. So this is sort of how far away we are from the string amplitude. And of course, in this product, sometimes we might get terms that look like ui I plus 1, which are exactly associated to sort of edges that lie in the boundaries, and these we set to 0. Okay, so let's see why this polynomial satisfies what we want. So to see this, let's sort of understand what happens when we're probing a factorization associated to some chord where we cut the surface through some chord ij, okay? And so we note that if some particular triangle, T star, intersects it, just like the one that I drew here, right? Then when the uij goes to 0, which is what we know happens when we're probing the massless singularity, then there's definitely going to be at least one chord that corresponds inside the triangle, right? 1 km inside the T star that will intersect ij, right? So here we see that for this particular triangle, there are actually 2, right? Which tells us then that ultimately, for that respective km that intersects, we know that the u variable associated to km will have to go to 1 just by the u equations, right? So if uij goes to 0, then ukm has to go to 1, which basically tells us that this product that appears here associated to that particular triangle, to T star, is going to go to 0, right? And so ultimately, this polynomial, when uij go to 0, the terms that correspond to any triangle that intersects automatically just gives us 1. And so in the end, the full polynomial kind of factorizes into the product over the triangles that live on the left smaller n-gon times the product over the triangles that lived on the right smaller n-gon, right? So which are respectively the sort of smaller pn's, just exactly as we wanted, okay? So this is a possible such deformation that we can build. And this one actually just very easily generalizes to any m-gon that we can define inside the n-gon, the polynomial, the momentum, the momentum n-gon. Okay, so like now for general m-gon, this now corresponds to just a collection of m different vertices of the polygon. And so we do exactly the same thing. So while before we had a product over all the triangles, now we take the product over all the m-gons that live inside the polynomial, the polygon. And then we further take this extra product where now the I and j are just pair of indices that we can take out of these m different vertices, okay? So we can already see that like sort of an interesting feature that we can see directly is that if we make the m-gon sufficiently large, right, then at lower points, we're not going to be able to tell the difference, right? Because if the m-gon is really large, then it might not fit if we're just at 4 points and we take like pentagons. Then at 4 points, this like our answer just agrees with the string amplitude, but at higher points, it's when it starts disagreeing, okay? And so this is, well, in exactly by the same region that I explained for the triangle, this obeys massless factorization. And in the paper, well, what we've explicitly checked is for the case where m equals 3 and m equals 4, we can already rule them out just by asking for this consistent massive factorization up to level 1, as long as we check diagrams at up to 6 points. And another kind of interesting feature to point out is that once more, if we just, for m equals 3, so where we consider triangles, if we only had access to the 4-point amplitudes, in general, we will need to go to a very high level to be able to sort of exclude this theory. Like, so if we want to, because as we go to higher and higher levels, we sort of reduce the value that G can take, that the deformation parameter can take. And if we really want to nail it down to string theory, we need to go to very high energies. So to very high levels, sorry. So this is sort of just to highlight how going to higher points, like just showing how going to higher points gives us a much more efficient way to just rule out these sort of deformations. Okay, so I'm going to finish here. I think I've reached my time. So just as a summary, the sort of main lessons that I hope I was able to transmit is that these sort of different positive parameterization of the single integrals together with the u variables are really the variables that are tailored to properly do the study of the resonances of the string amplitudes, and as well as what goes to sort of killing possible deformation of string amplitudes, that these constraints coming from consistent multi-particle factorization do indeed impose stringent restrictions on what are the possible consistent theories that we have. And so here I just have some possible future like questions that we can ask, is that if indeed we can sort of extract these residues systematically, is it possible to like build up the full string spectrum? So there's a few new features that show up as we go to higher levels, like we know that there are degeneracies and so on. But maybe using the residues, we might be able to like build up the spectrum in this way. And ultimately, just a sort of more basic question about, on the deformation side, whether there's any sort of P of U-like deformation that will survive the constraints coming from massive factorization. Okay, so this is all I have to say. Thank you.
Thank you.
So,
time for questions.
Do you know of any exact model that you can read from their information? Like some sigma model that you know to solve exact CFT and then try to see if when a parameter becomes very small?
yeah, no, I don't know of any model.
Is it why did you propose that? I mean, is there a reason?
So you mean like this particular P of U deformation, you're saying?
Yes.
Yeah, well, yeah, I don't know if it comes from any sigma model. I'm just saying it's a natural thing. Like when you know about the variables, if you just want to come up with some object that like satisfies the first, so like all the properties about Regge behavior, the asymptote, like being soft, like exponentially soft at high energies are all there. It also has the infinite tower of states, and it satisfies massless factorization, which are the sort of the way people come up with candidates for deformations. This is just to illustrate that using these variables, you can come up with like deformations in a very simple way. The question is whether you can exclude all such deformations or not. But there's no motivation of whether it comes from a sigma model or not.
And also the other question I want to ask is there any hope to do this for closed strings, or how hard is it to
Yeah,
go from?
that's a great question. So for closed strings, right, where like the integrals are over the z's and the z bars, right? Like so it would be nice to understand whether there's some analog of like u variables in some nice way. Also, when we actually performing the integrals, the place where the z integral converges is different where the place where the z bar integral converges. So even just extracting it, like defining them by analytic continuation is much harder than in the open string case. So the question is more challenging there. That's a natural thing that we would like to understand, whether there's some sort of similar technique that we could use to extract closed string residues, but we don't know the answer. But that's definitely a very natural thing to think about.
More questions?
So in the unitarity constraints that you showed for the 4 points, so you only show the constraint coming from spin 2. What happens if you consider the spin 4? Well, no,
Sorry.
yeah.
What did you?
I meant instead of spin 2, I meant first level.
The set of what? Sorry, I can hear you very well.
Okay, so if you go to your second slide or third, yeah, that one. Yeah, this one. So here you're just considering the first level, right?
Yes.
Unitarity. So what happens if you consider the higher level?
Yeah, it seems this d minor smaller or equal than 26 is not changing. It's always going to be like that. Like you might have, so basically what is going to happen in general in this plot is that if you go to higher levels, it is always the case that you just are going to kind of make these edges, move around. There's going to be some special points that will start carving out a little bit better, but the sort of bound d small or equal than 26 is always going to be like that. At least with this particular plot was made to like level 3, up to level 3. And if you include that, plus also you can also just ask, because you'll also have some constraints in the dimensions if you just go from, well, anyway, you can do this at 4 points. You can also do the same plot at higher points. It's like, and gives you, like, it changes the region, but for alpha naught equals -1, it's always the case that we have this line. I don't think we can shrink it in the other direction. I think that's what you're asking, right? To really like nail that it has to be exactly equal to 26. Is that what you're asking?
Yes, and I also want to ask another thing. It's more of curiosity. Can you express can you go one slide before?
Yes.
Okay. Can you obtain an expression for a n? For a n in terms of an integral against in terms of an integral against Gegenbauer and an amplitude and the amplitude, the 4-point amplitude.
Yeah. So for 4 points, you can do that. The way I think the most efficient way to doing this is like, so if you extract the nth level like residue, right? Then you like so what happens is that if you're at n level, like the sort of contributions of different spins can kind of, so you extract residue of nth level and then you fix the coefficient corresponding to the highest Gegenbauer, right? So the corresponding to spin n, let's say, right? Like the sort of highest spin that you're exchanging. And then you can like fix the remaining ones by sort of going step by step. Like, so you first fix the highest one, then you like fix the next one and so on and so on.
All right. Okay, that's one way to do it. Another way is just use the orthogonality condition of the Gegenbauer.
Exactly. Yeah, exactly. Yes. So another way of doing that, it's the orthogonality condition. But as far as I know, I think it's more efficient to do it the way that I'm describing. You can definitely do it via the orthogonality condition. But well, I guess it's equal. Then you have some integral over cos theta in like high powers. It's just probably it's equal. Yes, you can do that in the way that you're describing. Yes.
Yeah, my question was, do you know if an efficient way of doing that? But I guess you said, yeah, there's no way.
Well, yeah, the way that, yes, I like in general, yeah, I would do it in this way, where I first fix the highest one and then I go to like the one before and so on and so on. But yes, that would be the way that I would do it. I don't know of a more efficient way to do that.
Because if you were able to do the integral, if you are able to do the integral generically, you would be able to obtain a n for n generic, right? In this way, you're doing n by n.
Well, exactly, but you need to always like extract the residue, right? It's not that you can just put it against the amplitude, because you first need to go on the residue, always. Right? Like you only have this expansion when you evaluate the amplitude at the residue.
Right, okay, but you
always need to fix an n, that's all that I'm saying. Like you need to ask for a particular residue to fix an n, and then for that particular n, there's such an expansion.
I agree. I guess you could still obtain you could leave n generic in that case.
Oh yes, you can definitely do that. Yes, you can, like, so you, because at 4 points in particular, right, you can predict, like, it's just a beta function. So like when you take the residues, you can like really just come up with the general form of the residues, right? And then you can like fix them in this way. Yes, yeah, you have a general form, exactly. Yeah, but then, yes. So, but then for a particular n, you leave n generic there, right? But then for a particular n, you need to fix like first the highest power, and that one you can probably match.
Yeah,
right?
yeah.
That would be how I would proceed. Yeah.
Yeah. Other question is how efficiently can you obtain the residues for the 5 points?
Yeah. So it's really like once you have the expression of the integral, as you go, like even if you want to obtain residues at higher levels, it's always something that takes polynomial time, right? Because it's literally a function that you're just extracting a linear coefficient or like some coefficient in the series expansion. So it's really efficient. Sorry, like, so is this clear? So maybe I can, let me go back to this integral representation. So even at 5 points, right? So just so that we have an example concretely to look at, maybe here's clear. Oh, let's look at here. So these C's are really the dot product of the two momentum. Okay, it's just a notation. Oh wow, what did I do? Oh, here. Okay, so the idea is that, so if I want to probe, so let's say I want to probe this when this is equal to like minus n13, right? Then my function is going to look like 1 over y13 to the 1 plus n13, right? Like times, and this is just some function in y13 and y14.
Yeah,
right?
okay.
And now you're just extracting a residue. So that means that you want to do some like series expansion in f in y13 small, and you want to look at the power of y13 to the n13, right? So you're just picking out a term in this expansion, and that's very efficient.
Okay.
That's the idea.
Any other question? What about loops? If you want to go for loops, what are the main problems that you see with all this story?
Yeah, well, the first thing is that people have not proposed any like deformations at loop level because the string integrals get exponentially more complicated. But I would say that it's still the case that, so that's, I think, the most, so these y variables, they were definitely known. Well, part of them were known before, but the sort of new feature that has been found is that now there's sort of a systematic way that given a triangulation, I can say go and just get the parameterization that is tailored to this triangulation. This was what was not known before. And similarly to what happens at tree level, there's a completely analogous story for loop level that I can, so at loop level, I'm just going to highlight the main features, right? So, oh, I'm sorry, I have some technological issues. Oh my God, what's the problem? Add page. Okay, it's going to be here. So at tree level, these integrals always look like I described this dy over y, right? And then we take the product over the c's, which are associated to all the curves in the surface, right? To the alpha prime and the corresponding kinematical variable, right? So at tree level, the surface that we're talking about, just as you asked before, is this disk, right? So really, we consider all the kind of curves that go from marked point to marked point. Okay, so at loop level, things get exponentially more complicated because, so even if we're strictly speaking just in the planar limit, even though there's a generalization for both the planar and non-planar contributions in the topological expansion, but in any case, just for simplicity, if we stick to like the planar contributions, now our surfaces start having punctures, right? So, but And the prescription is exactly the same one. We just take the product, so we still have a d-log form over the y's, where now the y's are triangulating this loop surface. So like there's now different ways of triangulating the surface, but the idea is exactly the same one. Okay. And now we still take the product over all the curves that live on the surface with their respective kinematic variables, right? But the sort of new feature that happens at loop level is that if I want to list all the curves that live in the surface, now I have infinitely many of them, basically because since I have a loop, now I can consider curves that go around the loop and self-intersect once, but also those that self-intersect twice, 3 times, and I cannot deform them into each other because now I have this puncture in the middle, okay? And so this is basically going to tell me that in this language of the U variables, I have really an honest, like infinite product of curves, right, over these self-intersecting curves, okay? And it's quite nice. This is a completely different way of representing the one loop answer of the bosonic string, but exactly because you have these infinite products of curves is exactly what generates the usual things that appear at loop level, which are these Jacobi theta functions and so on. Well, I don't want to get into those details, but it's a very non-trivial like change of variables to go from this representation to the usual way people write one loop string amplitudes in the, well, parametrizing just in terms of these z variables again. Anyway, so, but there's well, I guess the message that I want to say is there's also an avatar of this kind of parameterization at loop level. And once more, it makes extracting these massless singularity, like sort of extracting the residues is again very easy, okay? Like it becomes like fairly simple because it turns out that if you want to probe like different levels, you can like truncate this infinite product to the only things that will contribute. And again, it becomes a product of just extracting a term in an expansion. So it involves some more details, but I guess what I want to highlight is that even though we're not strictly speaking using these residues or what you would call leading singularities at loop level to like exclude deformations of string theory at the moment, because, well, it's harder to define this. There's not been really like define any deformations at loop level. If you were able to do that, these variables would still be the correct thing for you to like extract these residues. So a similar story holds at loop level, that just as a general call. Anyway, so.
Any other questions?
About closed strings, couldn't you use double copy since you know for open strings?
Yeah, you could definitely use double copy to do this. And like, yeah, double copy would give you some U bars, but it's still exactly because in the double copy, it has this sort of problem, which is that one of the integral converges in a region, the other one converges in a different region. So still exactly how you would access these residues, it's not super clear. That's the main reason why it's not obvious. But that's definitely something that we want to look into.
Just one last. About the, can you go to the 6-point case?
So like in the residue, in the matching.
Yeah, when you have the residue.
When I have the what?
Yeah, that particular slide. So is it known the now this function of the Gegenbauer for the topology that you have on the right?
No, yeah, no. It's actually already at like 5 points. You don't have. That's also a very interesting question that I've been trying to think about, which is at higher points, if you can do like, as well, we don't have like this sort of unitarity constraints, like coming from like partial wave unitarity. At higher points are like we don't have a natural basis on how to expand these things. So no, like here you're really like you're not expanding in some base. You're getting the residue, which is some function of the Mendel stems, right? Because you're scattering just scalars on the outside. And now you're matching them to what you get from gluing these things and like fixing the constants to be what they have to be so that the two things match. You're coming up with an ansatz, the most general ansatz that describes some like consistent theory that is made out of these simple 3-point vertices. And you're just asking whether there's a solution or not. But we're not doing so many like smart expansion in terms of like Gegenbauers or anything. There's nothing like that at higher points.
At 5, I guess there is.
At 5, okay, at 5 there is, but at 6 points, yes, exactly. But it's still at 5 points there is, which is like sort of if you localize on one of the poles and then you have you can interpret like as coming from the remaining 4 point, right?
Yeah, even if you localize it around the two poles,
You mean the Singularities function?
the ones that we have in our paper. The arginalization of the Deforming.
Yeah, but
That's,
it's not.
I thought you maybe always had to sort of at least think about the sort of an effective like 4-point problem associated to that. Well, anyway, yeah, you can do that. We're not doing that here. That's all that I'm saying. Especially because at 6 points, there's, as you're saying, well, for these topologies, you could in principle still do that, right? But not for this one, as you're just pointing out. So we're not like at the level of this matching, we're never doing that sort of expansion. That's...
Okay, any other question? Okay, let's thank Carolina then.
Thank you.
Thank you, Carolina.
Thank
Great
you.
talk.
Thanks.